Hi, I'm Mr. Russell, and we're going to learn about calorimetry and do our calorimetry lab with where we specifically will find the specific heat of lead. We'll use this little apparatus here that is a coffee cup calorimeter, and I'll explain more about it in a second. So this is what it would look like, and while it's set up, this is what it's going to look like as well. Now, just to warm up, just to make sure you understand the math or the theory behind this, if you could answer this question, if 800 joules of heat is added to 20 grams of water at 30 degrees Celsius, what will be the final temperature of the water? Now, if you have not done this and found about 40 degrees Celsius, then you need to go back and check this out. You would use the MCAT equation. Here's your heat, here's your mass, here's your specific heat. And this is your initial temperature. You're trying to find the final temperature. So if you're not familiar with that, go back and review the specific heat video. Now, moving on to calorimetry. So it's the process of determining the heat of a reaction or the specific heat of a substance is a branch of chemistry called calorimetry. The basis of calorimetry is the first law of thermodynamics, also called the law of conservation of energy. So what we're basically saying is that heat cannot be created or destroyed, it can only be transferred. So one substance or the heat is going on here in this reaction, we can understand that the heat of the chemical bonds in the chemical reaction is transferring to thermal energy, and we're measuring the thermal energy. So therefore, we can assume that the potential that is the same as the potential energy of the chemical bonds, and that's essentially what we're trying to do here. Now, those two previous slide had two different pictures of two different calorimeters. The first one is a bomb calorimeter. You don't have to know this one too, but it's basically just a steel container with a container of water with another container. That is where your reaction actually happens. It's ignited with lots of oxygen. It's kept at a constant volume, and the pressure is increasing. So the pressure, and it will heat up the water, and then we're measuring the temperature of that water. All right, and then another steel container for protection and also for insulation. So now, what we're going to do in our high school class is going to be use a coffee cup calorimeter. Essentially, you have your insulated container, you have your water, and your reaction is going to occur inside the cup, and then you will just measure the temperature of the water. Now, what's going to happen is, imagine you take a hot something, right, that's on the outside, and you place it inside. The heat is going to expand. The heat is going to leave the substance and heat up the water, right? And so we can determine the initial temperature of the water and the final temperature of the water, and we're able to make some conclusions off of this. So if we think about it, a sample of iron having a mass of 93.3 grams is heated to 65.68 degrees Celsius. It's placed into 75 grams of water, raising the temperature from 16.95 degrees Celsius to 22.24 degrees Celsius. Find the specific heat capacity for this iron sample. Now, this is just like what we're doing on our lab, okay? Now, you're collecting all this type of data here, and you have to make sure there's other data that is implied that you have to pick up as well. Now, we know that since the iron was heated up and it's hot, and it's placed into the water at 16.95 degrees Celsius, it's going to increase the temperature of the water, right? Well, the temperature of the iron is going to go down. So the heat is leaving the iron and going into the water. So we can say that the heat of the water and the heat of the iron are actually the same thing, but just in opposite quantities. Okay, the heat is leaving the iron. That's why it's negative, and this is a positive. Positive, it's increasing for the water. All right, it's leaving the iron, going into the water. Now they're equal to each other because of the law of conservation of energy. Now we know that Q equals MCAT, so we're just going to change Q into MCAT. And so we have negative MCAT equals MCAT, right? Now, we know the mass of the water, and we know lots of different stuff. We know the mass of the water is 75. We know the specific heat of water is 4.18. That's not given to you in the problem, but that is a constant that you should know, and it's 4.18. Now, the temperature of the water went from 16.95 to 22.24. So the change in temperature is an increase. So that's why it's a positive number. And now the over here on the right, this is the mass of the iron. The specific heat of iron is what we're trying to find. And then the change temperature of the iron is something you have to imply as well. It started at 65.58, but it is changing, and we assume that the final temperature of the iron and the final temperature of the water equilibrate when they are the same temperature. So that is one thing you have to throw in there. Now, the temperature of the iron went down. That's why this term right here is negative. Well, it's a good thing we have this negative out in front to cancel that out. So what's going to happen is you start to solve for the specific heat of iron, and using some math, I condensed everything on the left side and I left the right side the same. And so now I'm going to condense the right side, and now I can find the specific heat of iron is 0.41 joules per grams degrees Celsius. This is just using a coffee cup calorimeter. I can look right here, and I can find on my table in my notes that I have 0.449 degrees joules per grams degrees Celsius. That's actually Kelvin, but degrees Celsius, it's the same increment, so it's not an issue. Now, so I had 0.41 or 0.449. Well, this one is using the most complex and efficient methods, and the previous example was using the high school method. So what's going on here? Why do we have the difference? Well, there's a bunch of things you should consider. You should consider the purity of the sample. Is the sample completely iron? Well, in a high school lab, it may or may not be. We assume that the water was pure, okay? We assume that there was no heat loss to the surroundings, okay? And that is actually a big thing, something because no matter how well insulated it is, you will have some type of heat loss. And we also assume that all of the heat was transferred to the water, okay? There may be some air in the calorimeter that could also have absorbed heat. So that could have been different as well. All right, so these are assumptions that you should take into account as you do your experiment. Now, I'm going to throw in one more example. This example is in your notes. What is the resulting temperature when 35 grams of water at 75 degrees Celsius is mixed with 15 grams of water at 15 degrees Celsius? So the cold water and the hot water are going to mix together, and they are going to equilibrate. Now, the hot water is going to give its heat to the cold water. So that's why hot water has a negative value, okay? Now, so the hot water is the one at 75 degrees Celsius. Let's do the MCAT. And then let's start to try to plug in some numbers. Now, this is our hot water, and it was 35 grams, and it started at 75 degrees Celsius, and its specific heat is 4.18, okay? And keeping that negative there. Now, the cold water is 15 grams. Its specific heat is 4.18, and its initial temperature was 15. Now, their final temperatures, since they are reaching the same final temperature, they are going to be the same. So we can keep this variable and this variable as the same. TF are the same. So we're eliminating the 4.18 since they're both the same on both sides. And then let's get rid of those. So we're going to distribute the coefficients. We're going to distribute the 15, and we're going to distribute the 35 to make this. And then we'll combine like terms and get that. And then now we'll isolate TF to get 33 degrees Celsius. Now, does that make sense? Yes, it does, because it's somewhere between 15 and 75, right? You can't just cut them right in the middle because they have different masses. If they had the same mass, you would be able to put it right in the middle, the midpoint. But since you have you're going to end up with 33 degrees Celsius.
Now that we've understood how calorimetry works, now let's see if we can put it into practice and collect some data. So we have just a fishing weight here that I'm assuming that it is 100% lead, but it is lead. Close enough for government work. So it is going to be 52.42 grams. So I'm going to take the lead, I'm going to heat it up to 100 degrees Celsius because this water is 100 degrees Celsius. It's boiling water with the Bunsen burner. So I'm going to tie it in here and so that it's not touching the bottom because it might get a little hotter than 100 degrees Celsius if it was touching the bottom. Okay, now that we have this boiling and going to 100 degrees Celsius, the lead is probably already there, but we're going to go ahead and prepare our water. Now the first step is, I'm not talking about the water that's in this beaker. No, I want to measure into this calorimeter. This is my calorimeter here. It's got just an empty coffee cup. Now on the top I poked a hole in here so that I can put the thermometer in it. And it's got my digital readout here. I'll show you in a minute. Now, I have, the procedure says to take 100 grams of distilled water. Now I put it in here, and then you can notice that there's a little bit of bubbles right here. And now the bubbles are probably from, it was a little soapy on the inside, so you may have some soap or some impurities in this water. That could change your specific heat of water. So there's a lot of errors or experimental errors in this experiment that I want you to try to be able to see. We assume the purity of this lead, right? I pointed that out. We are assuming that this is 100 degrees Celsius in this beaker of water. And then now we're also assuming that this is pure water, okay? Now, this is 100 milliliters of water, which should be 100 grams. So let's go ahead and make sure we get an accurate and precise mass of our water. So we'll take this and we will, I put it in the cup. And the mass of our water is actually going to be 99.62 grams. It's pretty sweet, Mr. Russell, right? 99.62 grams. So I won't need this balance anymore. I'm going to put this off to the side. And now I need to take the initial temperature of this water. So I'm going to hold it into here so that it won't fall over. I don't need this anymore either. So my initial temperature right here is 23.1 degrees Celsius. That's the initial temperature of the water. 23.1 degrees Celsius. So there's my lead. I'm going to take this and I'm going to put it from here into here as quickly as I can. Alright. And now, the heat of the lead is now transferring into the water, and the temperature of the water is going up. Okay, so now I'll just sit here and stir so I can try to evenly distribute the heat. Okay, so I tracked the heat change, and surprisingly, the heat of the water only went up by 1 degree Celsius. So the final temperature of the water is going to be 24.1 degrees Celsius. Now, the lead and the water equilibrated, so the final temperature of the lead is also 24.1 degrees Celsius. From there you can calculate the delta T, the change in temperature. That would be your final minus your initial. And then your specific heat is going to be, for water, is 4.18, okay, joules per grams degrees Celsius. Now you have to calculate the specific heat of lead and I want you, that's part of your calculations, and I want you to calculate the experimental error. Now, I noticed a few times an assumption at some point, somewhere, and so keep those in mind as you answer your plus lab questions. And there is one other crucial source of experimental error that I have not mentioned yet, but just remember, if I hold a hot cup of coffee in my hand, will I still be able to feel the heat from that hot cup of coffee? Think about that one. Okay, there's your clue. All right, so have a good day.